Welcome to JACS in Conversation. I'm delighted for this session to have Professor Ruchi Anand of the Department of Chemistry at the Indian Institute of Technology in Mumbai. Professor Anand obtained a Bachelor's of Science from Delhi University and then went on to complete a Master's of Science at the Indian Institute of Technology in Kanpur. She traveled half the way over to obtain the doctoral degree from Cornell University. She then went on to do a postdoc as the Howard Hughes Fellow at Sloan Kettering, followed by the University of Pennsylvania Wismer Institute. In 2008, she was appointed as assistant professor at the Indian Institute of Technology in Mumbai. She quickly rose through the ranks, where she is currently professor of chemistry at that same institution. She is the recipient of numerous awards. I'll keep the list short. The Mobility Award from Northwestern University, the Bach Havat International Award. She's a member of the Asian Chemical Biological Institute, member of the Indian Biophysical Society, the Asian Crystallographic Society, the National Academy of Sciences, Chemical Research Council of India, and a Wellcome Trust Senior Research Fellow. Her research spans quite a number of different areas, but it's largely focused on gaining structural insight into protein regulation. You can correct me if I'm wrong in a second. And with a focus on the origins of antibiotic resistance, understanding regulatory switches. She has also done research on nucleobase deaminase and biosensors to detect pollutants in water. And to that effect, she is a member of the Editorial Advisory Board of ACS Sensors. So welcome, Ruchi. It's great to have you here.
Thank you, Eric, for this lovely introduction. And I'm very glad to be here.
Let me start off with a very simple question regarding your origins. You were born in India and obtained your primary education as someone young in India, and then traveled the world over doing cutting-edge science. What was that experience like?
It's a very broad experience, first I'll say, because you grew up in one country with a culture, with views of some kind, and then you travel all across the world, and you end up in a different place, in a different culture, both scientifically as well as the way things operate in both countries. So I have to say that has made me much more broader in my view in life in general. Putting science aside, even in life, it is experience by itself. But I would like to point out that I came from a very small town. It's become a medium-sized town now, Dehradun, which is at the foothills of the Himalayas. And I grew up hiking a lot, being in the Himalayas. And this particular place is also very well known for its schools. So I had a good education early on. I went to Catholic schools and I was in one of the schools. I was shifted to one of the schools as a undergrad, 11th, 12th grade before my high school was finished, where most of the people go there to do engineering. And that's a big thing because in India, you can either be an engineer or a doctor. And that is what the premise is. And in that respect, I was in this engineering section with 50 boys, actually, and 7 girls. So it was a very competitive environment I entered. And I kept on asking myself, I don't want to be an engineer. And so why am I doing this? Because most of the things, however, we learned was science, basic science, physics, chemistry, math. And I was glad I was in that environment because I was able to rigorously study those subjects. But then I was able to choose what I want to do from there. And I went to Miranda House, which is a Delhi University college, to do my undergrad. And I had some of the best teachers there. I really, really got to know that I liked chemistry so much there. I had some very good teachers like Amrita Sheikh and Bani Roy who really taught me both quantum chemistry and inorganic chemistry. And I really got into both these subjects. And that's how I told my father, who was also a scientist. So I did have some background of science, that I would like to go to IIT Kanpur, which had a very good chemistry department at that time, for my master's. And that's all, and that's the only place I want to go. And I was very lucky to get in there because I was able to now understand that just learning your subjects is not the only thing. What is research? What research actually means? I could see professors who would teach and do research. And you can see I'm living that life today because I got motivated at that time.
What was your experience as a young faculty when you came back from your postdoctoral studies and you started your independent career? What was that like?
It was a difficult experience, let me put it this way, because when you are a postdoc or a PhD student, you're responsible for only yourself. You're doing your research project is your life, and you don't have to worry about how to get the money. You don't have to worry how to get the equipment in your lab. You don't have to teach. You don't have other managerial roles and duties. But the minute you become a faculty, things are different. Now you're responsible for other researchers and you're supposed to teach them how to do research and to shape their careers. That's a big responsibility. So, and then I had done most of my research in the US and I had landed up in India. And to adjust to understand the local system, it took me some time. But then everything kind of fell in place as it does over time if you keep at it. And I would like to mention one more point. I entered this department and I was the only woman faculty at that time. But our department has really grown and now we are 4 of us. So I'm not alone anymore. But for the first 7 years, I was the only one. So yeah, it was a little difficult, but I think it is difficult for everyone.
And who were your mentors? Who were your heroes as you were sort of charting out on your independent career?
So I would separate the two, let me say. My mentors are my mentors, and then I always had some heroes. And I'll tell you why I'm separating it out. But the mentors, my PhD supervisor, Steve Illick, was my greatest mentor. Till date, he taught me how to think about a research problem, how to execute it, how to write it, how to even, later I was also involved in grant writing in their lab a little bit. So I got exposed to that. He gave me an overall holistic education, taught me concepts. So I am very, very grateful to Steve for his contributions. And in general, at Cornell, I had scientists such as Barbara Baird, Brian Crane, and Tag Begley. And we had, with Tag, we had a close collaboration also. So they really were very good mentors, I would say. They were really, you could ask them questions. They would, in your committee meetings, they would ask you questions. They would be inquisitive about your project. You could go and talk to them independently. And they taught me a lot. And they made me what I am today. So my mentors, Johanne being one of them, is really been very important. I've been able to learn tenacity and dedication from her. We had a Puring group where Janet Smith was a part, and I collected some data in Kathy Drannon's lab. So she was young and dynamic, and she really influenced me, like a role model. But other than that, I from childhood as heroes. I always had these. I really thought Madame Curie or Marie Curie, let me put it, was the most fantastic scientist, that was ever there. Her dedication to science was just amazing. So she was my biggest role model, and Rosalind Franklin being another one that I always look up to. Maybe because I am in the field of X-ray crystallography, some of them are closer to my heart, I would say.
So, Ruchi, I wonder if you could tell us about your science. What kinds of questions are you dealing with at present that you're really excited about and dying to get out there and give lectures on?
I was very interested in understanding antibiotic resistance, and I am doing that now. And more than anything, I always like to look at the molecular level of why, how, what. And that's why the focus that we are currently having, and which I was nudging towards, is to understand origins of antibiotic resistance. What I'm trying to say is, why do bugs who would otherwise just die of our antibiotics, they become superbugs. What happens? And can we then perhaps curb it? So one way to tell about antibiotic resistance is to look where they've come from. And 70% of the antibiotics have come from these soil bacteria, and they know how to make the antibiotics and also how to protect themselves. So when I started, I looked at streptomyces because I know that they are the evolutionary heroes in the subject. They are the progenitors of all the resistance mechanisms. So that's how we studied that. Currently, we also do efflux pump regulators, but we are looking at ribosomal methyl transferases. And the problem that we're looking at is this methylation reaction is a very universal reaction. You will see DNA methylases are there in chromatin remodeling, so gene regulation, chromatin remodeling. And then when you come to antibiotic resistance, lo and behold, they are still there. Right? But then if I were supposed to develop an inhibitor, and if it's a S-adenosine methionine dependent reaction, they're all over the place and many of them have similar catalytic domains. So the question I asked is, how does this little enzyme know I have to go to this spot in the ribosome, methylate it there and nowhere else? So there's information embedded in them which tells the biological system, this enzyme, small enzyme, I have to go to the ribosome, methylate this particular base and out I go. So the enzyme knows it. So our question is, how? Where in the enzyme is this information embedded and how does the targeting mechanism happen? So one way to stop an enzyme from functioning like for resistance is you don't let it go to that spot. So that's what we worked on a little bit, and we are trying to expand it much more. That particular work, actually, we had published in JACS a couple of years ago.
What's your second focal point that you wanted to comment on?
Yeah, so I mean, it looks a little bit far off, but it is actually not that far off, the biosensing work. That particular enzyme is also got a lot of allostery in it. And the way we got interested in it was a switch, I can call it that way, that it would turn on. During environmental stress, it would turn on RNA, sigma 54 RNA polymerases and degrade environmental pollutants, for example, or any stress related. This is how we got interested. Then we realized that this system was just such a nice allosteric system, which I don't talk about that much. We are trying to now study it. But we also could develop really nice biosensors. We could engineer enzymes it was a phenol sensor that we started with. We could engineer it because we could do structure-based design and make it benzene sensor, toluene sensor, and we could engineer it to be even, mescaline sensor. So many kind of sensors we could make it with it by using a structure-based design approach. And we were able to finally fine-tune it using synthetic biology with to low ppb for drinking level limits even.
What's the readout for the sensor?
It's a fluorescent readout. It's a fluorescent
okay.
readout. There is a colorimetric readout, there's a fluorescent readout, and now we are developing devices which is ongoing work with electrochemical readout.
What advice would you give someone young who's starting out?
You are supposed to find your own path. And instead of hurrying up and doing the same thing that you did in your postdoc and never having an identity of your own, take it a little rough. Try to find what you would like to do for a long time, and you enjoy, and you can forge a way, and you have to stick with it for a long time, right? So I would say let it be a little rough, be a little slow in the beginning, choose your problem wisely. When I say wisely, not something that you're not passionate about, but what your resources are and what you can do at a particular time. Be grounded in that way. It is going to get better, and you are going to do exactly what you want to do. Maybe if not today, 5 years from now. Just have a little bit of patience. But the most important thing is not to just start and say that tomorrow I have to publish 10 papers because otherwise I'm out of the game. This is where the trap lies.
You're absolutely right, Ruchi. It's not a smooth path, and it's not a straight line either, right? Everyone has their own obstacles to overcome, their own advantages, and I guess one has to figure out just how to balance those so you can chart a career path.
as a young researcher, you are going to be competitively entering whatever field you choose. So you have to perhaps read a lot and figure out. So spend a lot of time reading and understanding your problem and finding something that, with your resources, with the current lab structure that you have, with wherever you are in the world, you can make a mark eventually, even if you start small.
Can you think of ways, if you had a chance to rewrite the curriculum, the way we teach chemistry in high schools or at the undergraduate or graduate level, what would you do to make it different, to make it more effective?
Eric, when I was growing up and even today, the biggest thing that I feel is when the students are studying, they don't understand science. The people in my class, if I remember, when I was in my high school, they were some of the smartest people I knew. Apart from me, nobody went into science. So that is a shame, I think. Maybe if they knew what science was, they would have a different view of the whole thing. So I feel that in our curriculum, we should have not just the concepts, but being able to show people what science is, get popular lectures in more to popularize science, and also show science in some way, and have them start at an early age.
It sounds like you're a wonderful teacher. So let me follow up on that. How do we make the general public more appreciative of science, and in particular chemistry? It seems of the three areas, physics, chemistry, and biology, the general public gets chemistry least. They can appreciate physics and biology. Chemistry always has this problem. How do you think we can address that?
Well, if I tell you some of the very recent Nobel Prizes, the most exciting researchers have been going in chemistry. I shouldn't be saying that. I don't mean physics and maths are not doing. Maybe I'm a little biased. But that thing is not out to the public at the level that they should know that chemistry doesn't mean learning some, metals, or learning reactions, or, at the high school level, somehow we are missing like what I was saying, innovation. But in general, also for public, they are not able to grasp the whole essence of it. So if we were to give popular lectures or connect the results that were available, for example, popular Nobel Prizes, and how they got, and where's the chemistry, and what the molecular level information, and how they can connect at what they're studying in their schools and what they knew. I'm talking about general public. If we were able to, perhaps, maybe like a TED talk being more common in, all cities, and we can popularize it in some way, then I would think that people will not shy away from chemistry. Maybe we need to tweak our curriculum a bit to make it more exciting. Plus, we need to, get the information out there. Somehow there has been a disconnect. For physics, all kids, my kid, for example, he listens to these astronomy lectures and he's like, wow.
So, Ruchi, you've had an incredibly successful career to date. And I'm curious if you take stock of where you've been and where you are. Are there certain things that you are extremely proud of?
So, Eric, when you talk about something that I'm most proud of in my career is being able to mentor students and make them into individuals which they have their intellectual thought and their logical thought and their own research ideas completely developed. And and when I see them completely independent, I become really proud, because they come back to me later and they tell me that you played a great role. I have to say the same for my advisor. Till date, I feel that I become what I have. So being able to give that opportunity to people and to my students, for example, and is a big thing, and one of the most fulfilling things that I have in my life. It is more important than all the publications that one can harness. And I wanted to point out that in this world of competition, many of the students are more exposed. They get to go outside and they apply to universities. But India, with a very broad spectrum of the type of economical population, many of the economically challenged people, when they come, for example, to my lab, they are very bright, but they have not seen what research is. That's what I was talking about in my previous question that you asked. They become like, they bloom like flowers over the 5 years or 6 years of their PhD, and they become into fully developed research individuals, which is the greatest pleasure one can get. And obviously, because we are working on topics like antibiotic resistance and biosensors for water pollution development, if we can, like I was talking, really develop them into good systems that can be of good use, that also is some driving force that I always have in the back of my mind. I do like to do research, which is, let me put it, slightly selfish endeavor sometimes, because you're getting excited. But if you can give to the society at the same time and come up with something which can help the society at large, India and the world at large, it's a big thing. And even if I can do one drop in the ocean, I feel good about it.
So Ruchi, you're an author in JACS, probably a referee as well. And I'm curious, what do you think JACS has done well to date? And what can we do better as we move forward in this new era?
So what I like about JACS, what it has been done, is that you have a very well-rounded editorial board, editors, and they can understand the broad ethos of science. And it is these people who are handling the papers, and they're able to then send it to the right people for review, where you get very good suggestions. Sometimes, it's not only about publishing, it's being able to get good reviewing done on a paper. Many times you can publish afterwards. So this whole network that JACS has developed, I think, is something commendable. And then they're able to come up with a broad area of something that would influence chemistry in the long run, not just, very niche thing that you would have done in various regimes of chemistry. So that's what I like most about JACS.
So Ruchi, thank you for taking time for this interview. This brings us to the end of the interview today. It's been great chatting with you and getting insight into your vision for chemistry, the past, present, and future, your teaching philosophy. And so thank you. I know you have a very busy schedule, and it's great that you could take the opportunity to chat with us. And I'm sure this will be a video that'll be watched extensively on the JACS YouTube channel.
I'm much less busy than you, and you've taken out the time to chat with me today. And it was really nice to be able to talk to you and discuss things, life, science, and other things in general. And I really thank you for this opportunity for being able to talk in this forum.